All right. Any questions? Any comments? So this hour will be almost like an example problem, but it will be very simple, right? We are going to work on the simplest possible system. Let's consider so this is the simplest possible system we can imagine, right? Because like one level system is trivial, you cannot do anything about one level system. The next simple thing is two level systems. And sometimes people with computational mindset, they call these qubits. And chances are many of you are going to be working in those qubits because it's like a big enterprise at the moment. And also, to understand the quantum mechanics, in my opinion, two-level system is the key, right? Many complicated concepts in quantum mechanics can be embedded in a two-level system, and then if you understand in the two-level system, you understand in the general context. So here we have like an abstract Hilbert space, and in that abstract space we have two abstract states. Let's call them 1 and 2, right? So these are just states at the moment. Right? It doesn't matter what basis we are, it doesn't matter what notation we use, they are just two states, and I use ket1 and ket2 for these. And a general state, any state, can be written in terms of these states. So this psi, like in the Hilbert space, is something like this. Psi, okay, this is uppercase psi, is equal to some A1 plus B2. A and B are complex coefficients. Now we want to, what do we want to do? We want to represent this in linear algebra, right? We want to write matrices and we want to work with these matrices because we don't know what to do about abstract objects. And the way to do this, I can just say this one state, so this ket, can be represented with, I don't know, some column vector which is 1, 0. Right? This arrow means 1 is represented by this, and 2, I can represent it with 0, 1. And I can see now like 1 is 1, right? This is normalized. I can look 1, 2. What is this? Like I take column vector and do it like a row vector, 1, 0, and take 0, 1, and this is 0 plus 0 is equal to 0, right? They are like orthogonal to each other, they are normalized, and it seems like this representation is so far working. And in that space, I also need to have a Hamiltonian, right, H. And from the previous lecture, we said H is going to be represented, so this abstract object is going to be represented by its matrix elements, I, H, J, right? And because there are in total two states, this is going to be a 2 by 2 matrix. So this is, 1 H 1, 1 H 2, this is 2 H 1, 2 H 2. But you can see it is right a little bit ugly to write it like this. Let's just define some labels. Let me call this one epsilon 1. Let me call this one H12. These are just numbers. H21, epsilon 2. Yes.
Did you put a hat on purpose?
Yeah, these are like, I'm trying to say like, so these are abstract objects, right? This 1 and 2, the states. And my Hamiltonian does something to these states. and it is given by this, H hitting on 1. And if I take bra with it, this is like a number. And there's like one number here, and this is, right, now it is operator in the middle, but once I did all these operations, it is just a number. Another number here, another number here, and another number here. So I construct a 2 by 2 matrix by looking at what my Hamiltonian operator as an abstract object does in the space. But once I have this 2 by 2 matrix, I'm done. I can identify my Hamiltonian by this matrix. If you want, this is like a representation of Hamiltonian in this 2 by 2 basis. And there will be Schrödinger equation. Again, this is I h bar, this psi is equal to this h psi, right? And because an arbitrary psi is written in terms of these expansion coefficients a and b, which may depend on time, right? So derivative of a and b is going to be some matrix equation, right? H times a and b. And in a little bit, we are going to solve this equation. But what we do, what was our program? Our program is not to solve time-dependent Schrödinger equation, right? Our program is to solve time-independent Schrödinger equation, H psi, or like, let me say it like H S is some energy times S. We find the eigenvectors and eigenvalues, and we expand any other function in terms of eigenvectors, and we put the phase vectors depending on that. So physically, like we typically in nature, we don't have two-level system, right? There are some physical two-level systems, but they are coupled to other levels. But any complicated system can be isolated to two levels, right? Maybe I have like many levels, but I go to such a low temperature and such a low energy window, only the lowest two are going to be relevant, right? So we can do this for any system, and these two levels, let me call them, I don't know. I wrote it like this. So this one I call E times delta. This is E minus delta. Rather than E1, E2, I wrote it like this because it was a little easier to do calculations like that. Right? This is E1, E2. And if you remember from more elementary lectures, I don't know, maybe something can come in and there can be like some kind of coupling between these two things. Like this one, I'm going to just show it with delta. So the amplitude to couple the first state to second state is going to be delta. And each state is going to be epsilon 1 and epsilon 2. I think maybe the other way. Epsilon 1 and epsilon 2. And with this new relabeling, my Hamiltonian is going to be H epsilon minus delta, epsilon plus delta. Right? This is exactly the same thing, but I just redefined with some new labels. And so this is some delta, and this is delta. So Hamiltonian is Hermitian, right? If you take delta 1, delta 2, Hermitian is going to be transpose conjugate. For it to be Hermitian conjugate, delta 1 and delta 2 should be equal. So I just put the same number. Good? Yes?
Can you go about here, why didn't you write like the time limit?
Oh yes, I forgot. Thank you. Yes, I'm sometimes sloppy. I appreciate. Thank you. So what are we going to do? Like suppose, okay, here's the problem given in the book. It says suppose you start with a state 1, and under this Hamiltonian, right, this is going to be represented by 1, 0, and this is like your psi of 0. Under this Hamiltonian, this thing is going to go to some psi of t, and problem is asking us to find this psi of t in its 2 by 2 representation. What is a of t? What is b of t? Right? We start with this state, and evolve in time and have these complex coefficients. Right? And the program is what? We need to write this state, which is our psi 0, some A0 E1 plus B0 E2, right? We need to first find these E1 and E2 states, which are the eigenstates of Hamiltonian. Once we do that, time evolution is trivial. This is going to be A0 e to the minus I over h bar E1 plus B0 e to the minus I over h bar E2. There's also t here and t here, and E2. So this is the goal. We are going to do, what are we going to do? We are going to find eigenvalues and eigenvectors of this Hamiltonian. We are going to use eigenvectors like this E1 and E2 to express this state in the basis of Hamiltonian. Once we write that, we are going to put these energy phases, and the program will be over, right? That's what we do all the time. So that means we need to do a little bit linear algebra, and we need to know how to find eigenvalues of a 2 by 2 matrix. So let's do it. So the program is that we have this epsilon minus delta, epsilon plus delta, this little delta, this matrix is multiplying some u, v, there's like a column vector, and it's giving us some e, u, and v. Right? That's the eigenvalue problem. And the job is to find what e is and what u and v are. Because this is like a 2 by 2 matrix, there will be two different e's, e1 and e2, and they are going to have corresponding e1 and e2. So I think you can do your usual way, right? You are going to put like minus lambda here, minus lambda, and determinant. Let me just show you an alternative, just in case you never heard that. So there are two eigenvalues, E1 and E2, right? And so this is H. What is the trace of any matrix in terms of eigenvalues? Does anybody know? What's that?
The summation of 1 and
Exactly. It's like trace is sum over eigenvalues, right? So there's like some theorems, some very good mathematical theorems that prove this. Doesn't matter. Trace is E1 plus E2, and I look at trace, epsilon minus delta plus epsilon plus delta is 2 epsilon. So there's one information. The second information is determinant. What is the determinant of a matrix in terms of its eigenvalues? So if the trace is sum of the eigenvalues, what do you think the determinant is? Yes, product of eigenvalues. E1 times E2 is equal to, and product is what? E squared, E minus delta times E plus delta is E squared minus delta squared minus delta squared. And let me call this object, not to write over and over again, let me call this psi squared. Okay, just a shorthand so that I don't have to write all of these things. Then what I can do is, I can use the first equation and plug it in the second and solve it. Right? So this is what I mean is, E2 is going to be equal to, from here, psi squared over E1. Now I plug this in the first one. E1 plus E2 is psi squared over E1 is equal to 2 epsilon. Then I have E1 squared minus 2 epsilon E1 plus psi squared is equal to 0. And that's the quadratic equation. E1 is going to be equal to minus b is 2 epsilon plus or minus 4 epsilon squared minus 4 psi squared, and the whole thing divided by 2. And that thing, okay, is cancel this, cancel that, and you can see epsilon square minus psi squared, right? So epsilon square minus psi squared is going to be equal to delta squared plus little delta squared. Then my eigenvalues are epsilon plus or minus delta squared plus delta squared. You can do it for E2. Then one eigenvalue is going to be E1 is equal to epsilon plus delta squared plus delta squared, and the other one is the minus. Okay, this was the easy part, and the hard part is how do you find the eigenvectors. So this is E2. Actually, I want to write it like E1 minus E2 plus. Doesn't matter, I just choose labels as I want. So I have the eigenvalues. Now I need to find eigenvectors. What is the algorithm? So the procedure is just put this value in the equation. Epsilon minus delta, epsilon plus delta. So this is delta, this is delta. So this is UV is equal to, let's say this is E1. This is UV. And we also have normalization, U squared plus V squared is equal to 1. U and V can be complex, but let me not get into that. There's also a way to make them complex. For the moment, let's keep it simple and imagine they are real. So I can do the following. Epsilon minus delta times U, right? I need to find V in terms of U, and if I use this relation, I find U. If I find U, I find V. Then the program is over. So this is epsilon minus delta times U plus delta times V is equal to E1 times U. Then V is equal to E1 minus epsilon plus delta, E1 minus epsilon plus delta divided by delta U. And now U square plus V square is going to be equal to U square. I'm going to take 1 plus square of this object. So this is square, square. This is 1. This is an equation for U. If I can simplify it for U, I'm done. And I plug this in for V, and I find U, I find V, and I find E1 and E2, I'm done. But I want to just show you a little trick to write it nicely. So this thing is going to give us U square is equal to delta squared divided by, right? I take the delta square here, and I need to have here delta squared plus E1 minus epsilon plus delta squared. So this one, I want to write this denominator. So this piece. So I want to write it as epsilon 1 minus delta squared, epsilon squared plus delta squared plus 2 delta epsilon 1 minus epsilon. And lastly, I need to write delta squared. But if you look at the E, right, delta squared plus delta squared here, there's the little algebra, delta squared plus delta squared is equal to E1 minus epsilon squared. So then I can use this one, and this one is going to give me E1 minus E squared plus E1 minus where did I get it? E1 minus E squared. So these two plus I have these two, 2 delta E1 minus epsilon. Good. Then I can take E1 minus epsilon parentheses. So this is going to be 2 E1 minus epsilon plus 2 delta. Now I put this for U. Also, what is delta squared? You can see delta squared is epsilon 1 minus epsilon squared minus delta squared. So let's also write that. So E1 minus epsilon squared minus delta squared. I wrote the delta squared. Divided by this entire thing. So this one, let me write in 2 steps. Yes, so this one, I can take this out to write here. This is 2, this one also goes. And here okay, let me do it in 2 steps. So this is epsilon minus delta times E1 minus E plus delta. Okay, good. That's the part I want. So this one is going to cancel this one. And you can see this thing is 1 over 2 E1 minus epsilon divided by E1 minus epsilon is 1 minus delta over E1 minus epsilon. So this is my U squared. And if I have U squared, I have V squared immediately. How? V squared plus U squared is 1. So if I do this, I have the solution. Good. So a little bit roundabout, but this works. So what I want to do is now I actually have it more complicated form, but I want to simplify it. Suppose to make equations nicer, choose delta is equal to 0. This corresponds to the example in Griffiths. Example, I think I wrote it 3.8. In that case, what do we have? Delta is 0. I have 2 eigenvalues, epsilon minus delta and epsilon plus delta, right? If uppercase delta is 0, E1 is equal to epsilon minus delta, and E2 is equal to epsilon plus delta. And U and V, what are U and V? U, V is equal to 1 over root 2. So if delta is 0, I have either 1, 1. But I said there's like an overall arbitrary phase, right? And the way to choose the arbitrary phase is E1 and E2, their eigenvectors should be perpendicular because this is a Hermitian operator and its eigenvectors are complete and they are orthogonal. So the way to do this is this. And you can check, we can always check this. So let's see, epsilon, delta, epsilon times 1, 1 should give us, I think this is minus, this is plus. That's why you should always check. So if this is minus, I have epsilon minus delta and epsilon minus delta minus, and this is epsilon minus delta 1 minus 1. So this is check, and I think this one also works. Good. So what did we do? The program was first find eigenvalues and eigenvectors. We have now E1 and E2, and we need to express the given initial state in terms of these eigenvectors. So this is E1 represented by this. This is E2 represented by this. And the initial state is 1, 0. It is equal to 1 over root 2. Let me write this one plus this and see if it works. So this one plus this. So minus 1 plus 1 is 0. 1 plus 1 is 2. 2 divided by root 2 times root 2 is 1. So this works. And then, so this is psi 0 represented by this. Then psi of t. And that's the last piece. Once we write this, we are done. And once you have it, you can use it to calculate observables and stuff like that. So this is going to be 1 over, I'll combine these root 2's to 2 here. E to the minus I over h bar. What is the energy? Epsilon minus delta times t. And the state 1 minus 1. And the second one is e to the minus I over h bar. Epsilon plus delta times t, 1 and 1. Good. And after that, Griffiths is just combining them to write in a nicer form. Let's also do that. So I can take out this e to the minus I over h bar, epsilon t. And what remains is e to the minus I h bar, delta t, plus e to the minus I over h bar, something like e to the ix plus e to the minus ix. This is going to be cosine delta t over h bar. And the second one is the same thing with the minus. It's going to be minus I sine delta t over h bar. And this is psi of t. Good. Any questions? So the message is like the program is simple, but we should be able to do the calculations. The intermediate steps, they are also very simple, right? Almost everything we do is trivial, but if you combine many trivial things together, it becomes a little bit complicated because we cannot keep our heads around. So that's why it's good to be careful and do it at least once in your life. All right, thanks.